Hello everyone. Welcome back to the week 8 of NPTEL TL live interaction session for the Rapid Manufacturing course. The course ID for the course is noc22-me74. This is Palkin Gupta, PhD scholar and a PMRF scholar in Department of Material Science and Engineering, IIT Kanpur. The course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. I hope every one of you are enjoying while learning the contents of this course. In case you have any doubts, you can always ask them in this session. So let us begin with today's session. This week's content was mainly focused on the laboratory demonstration of the fused deposition modeling type of additive manufacturing technique. In the first part of the lecture, we studied about various 3D printing processes, and the rest 4 lectures were majorly concerned about the laboratory demonstrations or the actual physical setups that are prevalent today. Okay, so let us first begin with the different kind of 3D printing processes. Okay, so in this we'll see the technology, the advantages of this particular process, the technical challenges, the various technologies associated with this particular process, and some other printing processes, and then we'll just quickly revise through the laboratory demonstration concepts. So firstly, there are two kind of 3D printing processes which are mainly used to develop three-dimensional parts. Used to develop three-dimensional parts. Okay, so first one is direct part printing and the second one is binder printing. So we can clearly figure out from the names themselves that in direct part printing, the part is printed directly, and as a result all the material is dispensed directly from a print head. Here the part is printed directly. So the part is printed directly from the material. And the other one is binder printing. In binder printing, what happens is there is an addition of a binder or any other additive onto a powder bed. Okay, so there is a powder bed on which binder droplets or any kind of additive droplets are added, and that binder or additive helps in the consolidation of the powder, and which then forms the bulk of the part. So here the part is not printed directly, but it is binded with the use of binder droplets. Okay. Okay. So next we'll study about this technology. So here we have the schematic for this particular 3D printing process. There are different parts associated with this. First is first let us check out the positioning system. One is the XY positioning system, and this is the Z axis. So your inkjet print head or your binder printing head, this can move in the X and Y directions. Okay, so this can move in your X and Y direction. So suppose if this is your X, so this is your Y direction, and this becomes your Z direction. Okay, now from this inkjet print head, so inkjet print head, this is responsible for dispensing out fine droplets of the part material or the binder Okay, and these XY positioning system and this Z axis, they are responsible for controlling the position. So now here you see these are the binder droplets that are being dropped onto this powder bed. So as these binder droplets are being dropped, you can see this hut kind of a shape. This is being consolidated or solidified, this shape. Okay, and this lighter gray one is the unused powder. This is the build platform and this is your powder spreader. So as we know and we have discussed it multiple times, every CAD geometry that you want to print is sliced into multiple layers and then each layer is printed one by one. So in a similar manner, this hut is also sliced into multiple layers and each is a 2D layer. So when one layer is binded, then this platform, build platform is lowered. After printing of one layer, build platform is lowered. Okay, it is lowered, then powder spreader spreads out a layer of uniform thickness onto the platform, and then when this layer is again binded, uh, okay, when this layer is again binded, then the platform again lowers down and powder is spreaded. So this continues till your complete part is printed. Okay, so this was the basic schematic, and this is your actuation or the lead screw, which is responsible for raising or lowering the platform. Okay, so let us just briefly go through the 3D printing technology and some of the terms associated with it. So once a layer is printed, the powder bed is lowered, as I had been talking about, and a new layer of powder is spread, that using the maybe the counter rolling wheels or cylinders, okay, using the powder spreader or the rollers. Okay, then this process is repeated until the complete part or array of parts is completed. Until the part or array of parts. Array of parts is multiple parts arranged together on the build plate. Okay. Now, this particular technology features several parallel one-dimensional avenues for patterning. Okay, so this means we can generate patterns or one dimension patterns in one dimension using this particular technology. Now, this is also called as a line-wise patterning process. Why? Because this process can be easily scaled up, easily and economically. Economic factors are play a key role in deciding anything. So they can be economically scaled by simply increasing the number of nozzles. So as you have seen, this is your this screw or something on which your inkjet print heads are mounted. So you can easily add your more number of nozzle. Easily add more number of nozzles on this drive. So what it will do is it will basically scale up the process, or you can make multiple parts at a time or eventually speed up the process. So then this becomes even more economic, and hence it is said line wise patterning, because you are adding your print heads or nozzles in a line-wise fashion. Now this is a high deposition at low costs, high deposition speed at relatively low cost. So this is high deposition speed at low cost. Okay, so by the use of multiple nozzles, your speed can be enhanced extensively. Okay, by using multiple print heads, with the use of multiple print heads, you can even go up to higher deposition speeds and at low costs. So, okay, so I have at low cost. Okay, and at and at a lower cost, because this particular process doesn't contain any high power energy sources like lasers or something, like lasers in SLA or SLS or SLM. So the lasers are high cost devices which really cost a large amount of money. But in this, you doesn't need anything extra. There is just a simple nozzle and your drives. That can be a belt drive or a screw drive. So it is a economic process. The machinery itself doesn't cost much. So the part is then typically left in the powder bed after its completion in order for the binder to fully set and for the green part to gain strength. Okay, so when your part has been printed, then it is deliberately left in the powder bed for some time. Okay, this is left deliberately. So in that time, what will happen is your binder particles will uh, will hold your powder particles even more strongly, and it will set and fuse the particles together. So your all the particles, say suppose this is your powder particles. Now you have added binder. So binder is in the liquid form. Okay, so these are your powder particles. Now you have added binders. Okay, this is your binder droplets. So when you leave this part to set, what happens is these binder droplets will have enough time to seep through these pockets or areas or regions or parts. And when they seep through these, they will help in holding these powder particles together. Okay, and when powder particles are held more strongly, particles are held more strongly, okay, the green part, the strength of the green part increases. Okay, okay. So next is then we need to have certain post processing. Okay, so post processing of the particular part involves the removal of the part from the powder bed. So now the part has been printed and it lies inside the powder bed, and you have left it for some time for the binder particles to settle down. Now, for the use of the part, it is necessary that you take it out from the powder bed. Okay, so that is a post processing step. Now it can happen that some of the unbound powder remains stick to the part. Okay, so that you need to remove using pressurized air. So pressurized air will exert force on the unbound particles and will force them to leave their place. You see, it's just a powder which is not having any strength. And now, then there is another step which is to infiltrate the part with an infiltrant to make it stronger and possibly to impart other mechanical properties. So, your part can be a porous structure. Okay, so the part in itself can be a porous structure. Okay, maybe any kind of a structure with open pores or something like that. Then you can always infiltrate your part with a secondary phase. Okay, so that will help in certain amendments or additions to its mechanical properties and will also add to its strength. So adding some polymers may give it some kind of a flexibility, or adding some ceramic shell might enhance its hardness, or adding some metallic phase can enhance its strength, etc. So for these purposes you can always use infiltrant. Now the parts are always self-supporting in the powder bed so that support structures are not needed. So what happens is, suppose this is your build platform. This is your tank where your powder is. This is your build platform. Okay. Now you have some part which is having some overhangs. So maybe some this kind of a geometry. Okay. Or maybe a T kind of a shape only. So this is the geometry that you are having and you want to print this part. So now when the material is printed here, it should it doesn't have any support from the base. It's just a overhanging part. So this is your overhanging part. So and this overhanging part needs support. Such kind of overhang, typically greater than 45 degrees, require support at the bottom with the build platform. Okay, so now how to provide support, but you see there is much of unused powder or loose powder left here in the tank. Okay, so this is your loose powder. So this powder in itself acts as a supporting structure. So in case of any powder bed technique, this loose powder acts as support. So extra supports are not required in such a case. So this loose powder acts as a support. And any kind of extra support is not required. Now, parts can be arrayed in one layer and stacked in the powder bed to greatly increase the number of parts that can be built at one time. So suppose you want to print say a cube, a cone, a cylinder, and such kind of multiple paths. So what you can do is, suppose this is again your build platform and your tank. So you can arrange your paths in an array. So this can first can be your cube, second can be your cone, third can be your cylinder. So this is basically an array of multiple objects. Okay, so this is your array of multiple objects. So in such a manner, you can, when you arrange multiple paths in an array, you can increase the number of paths that are built at one time. Else what would happen was, you would have printed this cube individually, this cone in the second cycle and the cylinder in the third cycle. So then it would have taken a much longer time. If these were printed individually, it would have taken a much longer time. Okay, so we always try to minimize the time and maximize the use of the resources. Okay, so let us now go through what are the advantages of this technology. So each technology always has its advantages and disadvantages. Okay, so we'll go through the advantages of this particular process. Okay. Okay, so the primary advantages of printings are the low cost, high speed, scalability, and ease of building parts in multiple materials and printing colors. Okay, so how is it a low cost technique? This is low cost because the machine can be assembled using simple and general components like belt drives, screw drives, etc. And also, no high energy sources are required. Okay, so that means that is there are no high energy sources, uh, of lasers or something like that, which add on to the cost of the machine as well as the operation. Okay, so operating a laser consumes a lot of electrical resources as well. So it is a high cost process, both from the machine aspect and from the operation aspect as well. So then this is a high speed process. How it is a high speed process? Because the speed of production can be easily enhanced by adding multiple printheads as we have discussed in one of the previous slides also. Say this was your the XY positioning system, and here was your inkjet printing head, which was dropping out certain binder droplets. This was giving out certain, and this is your XY positioning system, and this was your inkjet print head. Okay, now what happens is, you can, this is your one single head, so you can add one more head here, you can add one more head here, so you now have three heads. So what will happen is your production rate or production speed will increase. Production speed increases to 3 times. So which is a huge number in the manufacturing industry. If you can even increase the production time or the production speed by like make it twofold of the previous one, then it is huge increase. So this is now 3 times. So it is a highly scalable process or a high speed process. And then you have the scalability. So in this context, what does scalability mean? Scalability means that the printing speed can be increased by adding another printhead to a machine, which is a relatively easy task, or possible it is possible to add larger amount of mass or larger amount of material over a considerable area in a shorter span of time. Okay, so these two terms are interrelated with each other. When you have high speed, your process is already scaled up, and when you have low speed, your process is already scaled down. So as high speed is associated with the production speed and addition of multiple print heads, scalability is also associated with addition of multiple print heads, which allows it to add the material quickly and in larger amounts and over a considerable area in a shorter span of time. So, for example, when one printhead was in use, you deposited 1 gram of material only. But now, when three are being used simultaneously, you can add 1 plus 1 plus 1 equal to 3 grams of the material simultaneously. Okay, so in similar amount of time, your 3 grams of material is being deposited. So that is what how you scale up the mass. Okay, now the fourth advantage is ease of building parts in multiple materials. Okay, so you can use polymers, metals, and ceramics. So this gives us a wide window for the different kinds of materials that can be used for this particular type of printing technique. Okay, and next is capability of printing colors. Okay, so previously there were no colors, or there were like very selective resins. Initially there was only amber or blue or red. Okay, or blue or red colors, but now certain machines are available wherein you can have multiple colors, like for FGM only you can have red, blue, green, pink, white, brown, black, and whatnot. You name the color and it is available. Now the cost of the machine is low. This has been discussed, like because of the absence of any high power sources like lasers, absence of lasers or any such sources. So these are the reasons why the cost of the machine is really low. And the printing machines, they can be assembled from standard components like these your normal belt drives or lead screws and normal nut and bolts. So you see, let us go back to the first slide. So you see here, no complicated parts are there. There is just a build platform, an XY positioning system which can be a belt drive or a lead screw, this printhead which is simply a nozzle. Okay, and there must be a lever to raise and lower this platform. Okay, so relatively simpler parts are required for assembling these standard components. They can be used. Okay, and now the part accuracy is also improving as for the advancements are being done, but still it cannot compete with the accuracies that are given by SL, stereolithography or fused deposition modeling. Okay, so specifically for larger parts, part accuracy, particularly for larger parts, is not as good as one offered by SL stereolithography or FDM. However, they are improving. However, accuracies are being improved as research is going on. Okay. Now, we have seen the technology and we have seen its advantages, but there are certain challenges, technical challenges that are involved with this particular kind of process. First is the formation of liquid material. So since we are dropping it in the form of droplets, the material should be in the liquid form. Okay, so if it is not in the form of liquid, then we need to suspend the particles in a carrier liquid. Okay, suspend the particles in a carrier liquid. It can be any suitable liquid. Then dissolution of material in a solvent. We can use any a kind of solvent in which the material dissolves. We can form the liquid material by melting a solid polymer or by making a formulation by mixing monomer or pre-polymers with polymerization initiation molecules. Okay, and polymerization initiators. Okay, initiators, which would then initiate the polymerization reaction and form a liquid formulation. Now, once you have the liquid material, then you can just put it in your nozzle and allow it to form droplets. Now, droplet formation is another technical challenge in this particular process. So, material must be converted from a continuous volume of liquid into a number of small discrete droplets. So, suppose this is your nozzle, okay, and it is filled with your liquid. Okay, now this liquid has to come out from this opening in the form of droplets. Now initially it will come out as a continuous stream, and that stream, this has to be broken down into discrete droplets. Now how to achieve this discretization such that it is uniform? This discretization should be uniform. These are your discrete droplets, or this is continuous stream. All right, now any changes to the material such as addition of any kind of tiny particles can dramatically change the droplet formation behaviors, and this droplet formation behavior is deeply associated with the material, the hardware that is being used, and the process parameters. Okay, and the third part is you have formed the liquid, you have formed the droplets as well. Now these droplets are going to stick to a substrate or deposit on a substrate. Now this deposition of droplets, it is controlled by the droplet flight path. So if this was your nozzle and this is your substrate. Now after the droplet has oozed out from this, it has to deposit on this substrate. So this is the flight path. So it greatly influences its deposition. Okay, so flight path is the path that it covers after its ejection from the nozzle and before deposition on the substrate. So this middle part is your flight path. The impact with which it drops on the surface. Okay, impact with which the droplet impacts the substrate wetting. Okay, how much it can form bonds, how good bonds it can form with the substrate. Like you see mercury, it doesn't bond well. Like you can see it just forms spherical balls. Okay, so it doesn't wet the substrate. And on the other hand, you have water which easily spreads out and wets out the substrate. So what are the wetting characteristics of the droplets with the substrate? They influence the deposition and the droplet velocity and size. So we have two major defects that are associated with this droplet deposition, and so first is the satellite defect. So in this satellite defect, when you have a big droplet and small droplets break off from the bigger one. So they just splash and then these small droplets deposit here and there, creating surface roughness and inaccuracy. Suppose you had this bigger droplet. Now this is it and there are certain smaller droplets and they will now deposit. So this is your bigger droplet and these are your smaller droplets which have deposited on it. So this will induce surface roughness. Okay, so this is basically these small ones they are called as satellites of this bigger droplet. Now another one is crown formation. So when the impact is very large or the droplet velocity is high, what happens is when the droplet hits the substrate, because of the high velocity and high impact, it rebounds and solidifies. So you must have seen water splashing out. So when it rains, it drops on the surface and that it rebounds from the earth's surface and forms a crown like shape. So if you can visualize, so if this is your droplet, now it has fallen on the substrate and after dropping it splashes back, so it forms like this. So this is the rebound. Okay, so this is your, and then it solidifies here only. So it solidifies as it doesn't get sufficient time to flow down back. Okay, so this now forms a crown. So this is a crown defect and this results in high surface roughness. You can easily correlate it with a rain droplet impacting the earth's surface and then rebounding from the surface. Okay, now in this droplet formation technology, we have two modes of expulsion. They are basically dependent on how the droplets are formed. One is the continuous stream, and the other one is the drop on demand type of droplet formation technology. Okay, so the distinction here is in continuous stream, the liquid comes out as a continuous column of liquid. The droplets comes out as a continuous column, whereas in drop on demand the liquid comes out in the form of the liquid exits the nozzle in the form of discrete droplets. Okay, so this is kind of this continuous column and this is discrete droplets. Okay, so now this is the schematic for a continuous stream droplet formation. Schematic for continuous stream. So in this particular technique, pressure is applied to the fluid reservoir so that creating a pressurized column of liquid which then ejects out from the nozzle. So this is a actuator. This is the actuator which applies pressure or vibrations or causes any kind of perturbations. Okay, then this is the drive signal. Okay, this governs when or what is the frequency of this actuation. Okay, this governs the frequency of actuation. Here, this frequency is equivalent to the droplet formation rate. Okay, so the frequency of perturbations or vibrations should be kept equal or near to the rate at which droplets are to be formed. So when pressure is applied, okay, this is the fluid column, fluid supply. So this is pressurized and a continuous stream is ejected out from it. So this is a continuous stream. Now this continuous stream is broken off into small droplets, broken off into discrete droplets because of Rayleigh instability. Okay, so this is then breaks off. Now these are the charging electrodes. These induces charge on these droplets. Say they have induced a positive charge. Okay, now when these charged droplets pass through these high voltage deflection plates, then they deflect as per the CAD geometry or the CAD design that has been given. So some travel to this substrate and some are catched by this droplet catcher. Whatever travel here gets deposited on the substrate and gets printed. So this was the continuous stream where it is broken up into discrete droplets because of Rayleigh instability and which is controlled by the frequency of actuation. Okay. In drop-on demand technique, individual droplets are produced directly. Okay, here individual droplets are produced directly. Okay, so over here individual pressure pulses in the nozzle causes the fluid to be expelled. So these can be created by thermal, electrostatic, piezoelectric, acoustic and other kind of actuation mechanisms. So these are the actuation mechanisms. So these actuations, these actuators, these type of actuators creates pressure pulses. Okay, So now when these pressure pulses are created, droplets are ejected out from this nozzle directly. Okay, so as the droplet is ejected and it is deposited on the substrate, and this substrate is movable so that droplets can be deposited at different locations. This is movable so as to enable the deposition of droplets at different locations. So let us see some of the actuation mechanisms. So first is thermal actuation. Here, this is your ink tank, this is your orifice, and this is your heater. So when the fluid is heated, there is a formation of a bubble. Okay, this is the formation of a bubble. Now, as it is heated and heated, this bubble expands. So it creates a pressure within this tank, creates pressure. Now this pressure forces out some of the liquid to move out in the form of discrete droplets out of this chamber. Similarly, in piezoelectric, so the deformation of the piezoelectric element is done so as to reduce the volume of the liquid reservoir. So this is piezoceramic. Okay. So now this is deformed. Okay, when this deforms, it reduces the volume, as was the case with bubble formation. Now since the volume is reduced, a droplet starts to form as some of the material starts to come out, and as this deformation continues, there comes a stage where this breaks off completely from the orifice and forms a complete droplet. So, by any method wherein you can reduce the volume of the reservoir and create pressure and force out the droplet, that can be used for DOD technique. Now we saw some other techniques also in the end of the first lecture. There was binder jetting. So here the initially this is a more 3D view of the schematic that we had seen in the first lecture. So this is the liquid adhesive supply. This is the inkjet print head. This is the print head, and this shows the motion in different directions. So this is X. Okay, this one is X. This you can say is Y, and this up and down movement is Z, in which this build platform is moving. So you see the bind. This is the powder bed where here this is the powder supply, and this is a leveling roller. When one layer is printed, this is lowered, and this powder supply chamber is moved up, and a layer of powder is spread using this roller, and then this inkjet head jets out binder droplets, and there can be multiple heads, which is then called as binder jetting. The next, in the last, we saw the schematic of a fuse deposition modeling. We have seen this multiple times. This is just a bit different in the sense that it is having two simultaneous feed of material. Two simultaneous feed of the material. So still now the schematics we had seen, we were only feeding one kind of a filament, but here we see two filaments are being feeded. This is filament 1 and this is filament 2. So this is your main part and this is just your support material. Okay, so this has lower strength, so that this can be broken off easily from the main part later. So then there are these pinch feed rollers. So here these are the pinch feed rollers, and their individual heating chambers. This is also a heated chamber, and this is a heated chamber for the part material. And then as per the CAD geometry, part material and the support material, they are fed towards this platform, and this part is built. As you see, this is white part is your main part and this black section is your support material. Now then we saw some actual 3D printers and their functioning. So this was a part of laboratory demonstration for fuse deposition modeling. So here we can see this is a Tech BV30 kind of FDM printer having two nozzles. So this is printed here, and in this zoomed view you can see this is nozzle 1 and this is nozzle 2. Okay, each are having their individual fans, cooling systems. Okay, and this is the build platform. This particular one, this is your build platform, and these are your lead screws for motion in Z direction, and these nozzles they can move in X and Y. So we were told that it is necessary to heat the printer bed, necessary to heat the printer bed before printing, so that it doesn't have sharp thermal gradients, so that the printed material can easily stick to the bed. Okay, so the nozzle temperature was somewhere around 200 degrees Celsius, and this bed was maintained at somewhat 50 degrees Celsius, and ambient temperature was low. So this material is having, since it is at 200 degrees Celsius and in a molten state, it becomes easy for it to stick if the bed is maintained at 50 degrees Celsius. Okay, so for proper sticking and to avoid any kind of warpage and other defects, it is necessary to maintain the temperature of the bed depending on the different kinds of materials. So the different materials that can be used as mentioned were ABS, which is acrylonitrile, butadiene, styrene, which is a kind of oil, and the other one was PLA, which is polylactic acid and is an organic polymer. So both of them different extruder temperatures and different bed temperatures. Now then we were made familiar with a slicing software demonstration of the slicing software for printing. Okay, so this was the software named as Reptier for this Tech BV30 machine. Reptier for Tech BV30 FDM. Okay, so we made a geometry in the lecture using this one. So this one was this plus sign was to add the object. Then this one was to copy the objects. This symbol, which you can see, this was to copy the object. So you can make 2, 3, 4 or n number of copies that can fit the bed. So this was the auto position. This is auto position. So using this button, it will position the object in such a manner so that it minimizes the nozzle travel path. Okay, this is the center object option. So this places the object at the center. This option is to scale the object. So either you can scale up or scale down as per the requirements. This option is to rotate. You can rotate the object. So suppose if you have a cuboid like this, you do not want to print it in this orientation, but in this orientation you can always rotate it using this option. This is to see the section view. Okay, when we do not have any information about the internal contours, so this section view option can be used to visualize any kind of holes or hollow geometries. Okay, and then this last option is the mirror. So this is easy, so you can mirror the object using this. And then we saw how to adjust the speeds of the printing nozzle, how outer layers are adjusted, how inner layers are adjusted, what infill pattern should be there, what should be the speed of the infill layers, etc. All these details were given out in the laboratory demonstration. To use an actual FDM, I would suggest everyone and request everyone to deeply go through them thoroughly so that you better understand how to use any kind of slicing softwares. Okay, so now let us begin with the sample problems for this week. Okay, so we'll go through them one by one and understand the concepts behind them. So the question one is the employment of printing technologies in the creation of three-dimensional products has has quickly become an extremely promising manufacturing practice. True or false? This is true because this has eased out. This has eased out the manufacturing of complex geometries and has reduced materials constraint as well. Now, question 2. Dash refers to a process where all of the part material is dispensed from a print head. Direct printing, binder printing, both direct and binder printing, or none of these. So in the very first slide we had studied about this. All of the part material is dispensed from the print head. So we have direct printing. So where part is printed directly from the material that is dispensed from the printhead. Okay, and in binder printing, part is made from the powder in the powder bed or the build platform, and the binder droplets from the printhead. So clearly in binder printing, only binder droplets are ejected from the printhead, where rest of the part material lies in the powder bed. Whereas in direct printing, all the materials that is used in the part formation is expelled from the printhead. So the correct answer is direct printing. Now question 3, dash refers to a process where the build is printed onto a powder bed which forms the bulk of the part. So this is in continuation with the last question, and we can say in when the when the part is printed from the material that is in the powder bed, we say it is binder printing because it is the binder that is ejected from the printhead that consolidates the powder into a full solid part. Now question 4, in 3D printing, the powder bed is raised and a new layer of powder is spread below it. Okay, please try to understand what they are saying. Sorry. So suppose this is your powder bed. Okay, build platform. And your part is above it. So suppose this is your part which is being printed. And now they are saying this powder bed is raised and new powder is being spread below this. So this is your new powder layer. This is false. This is of no use. Instead, what happens is this is build platform, or you can say your powder bed is actually lowered and powder is spread above it. So please make note of the words bed is lowered and powder is spread above it. So this is false. Question 5. 3D printing features several parallel one-dimensional avenues for patterning. This is true. Using this 3D printing or inkjet printing or binder printing, it features several parallel one-dimensional avenues for patterning. Next question. Since the 3D printing process can be economically scaled by simply increasing the number of printed nozzles, the process is considered dash process. So we had discussed this during this brief review of the week's content and as well as in the lectures. It is called as line-wise patterning. Question 7. The printed part is typically left in the powder bed after its completion in order for the binder to fully set and for the green part to gain strength. True or false? So this is true. I had explained you. Suppose this is your powder. And these are your binder droplets. So you need to allow some time so that these can seep through these gaps and then holds these powder particles together. Holds these powder particles together. So for this you need to allow some time. So this is true, and for that reason the part is typically left in the powder. So question 8, parts are self-supporting in the powder bed, so the support structures are not needed in 3D printing. True or false? True. This also I had explained. So I had explained it like suppose this is your bed, print powder bed, and this was the part that you wanted to print. So since these overhangs, this particular and this particular overhang, they doesn't have any support. So the loose powder that is below them, this loose powder allows them the support. support and base. And because of these, we do not need any extra support structures. Because of this, because of this, any extra support structures are not required. Okay. Now question 9. Which of the following are the advantages of 3D printing? Low cost, high speed, scalable, or all of these? So the answer is all of these. It is a low cost process as the high power energy sources are absent. It is a high speed process since you can add multiple nozzles or multiple print heads, and it is scalable as you can increase the amount of material deposited by increasing the number of print heads. So the last question for today, FDM printers are of much lower cost than any other rapid manufacturing machines. True or false? This is also true because FDM printers do not have any kind of high power requirements. So in FDM printers, you do not need any kind of lasers or expensive heaters. They just require normal resistive heaters. Okay, and uh, that just solves the purpose by putting your filament to the molten state. So these FDM 3D printers are of lower cost as compared to your stereolithography machines or SLA machines, SLS machines or SLM machines or electron beam using machines, etc. So the techniques that we studied this week particularly are low cost ones because they do not have any kind of lasers or high energy sources. So this was all about today's session. In case you have any questions, you can raise them or you can post them in the discussion forum as well. So I hope you guys understood what have been taught through in the week's content as what we had discussed in this interaction session. Okay, so does anyone has any questions or queries? Okay, so this video lecture will be available to you through YouTube recordings, and this presentations will be available through Google Drive links. Okay, so I think can we wrap this up? Okay, I think we can end the session now. Thanks everyone. We'll meet in the next session on next Saturday at 5 p.m. for week 9. Thank you.